Hello everyone, welcome to our first video in the Saga series. Today, we are going to explore how Oracle Sagas can manage complex transactions and ensure data consistency and integrity across microservices. My name is Vinay Pandhariwal and I am here to walk you through these concepts. In today's software development landscape, the shift toward microservices architecture has been significant, specifically for its flexibility and scalability. Yet, these architectural choice brings its own set of challenges, particularly in managing distributed transactions across loosely coupled deployable services. The traditional transaction methods, with their heavy reliance on locking and synchronization, impede performance and scalability. Moreover, achieving consistent data across distributed services isn't straightforward and requires complex solutions. Let's understand it with an example. Imagine building a banking application with separate microservices for handling different banks. Completing an interbank money transfer involves both these banks working together seamlessly. But what happens if something goes wrong during the request? How do we ensure all changes are reversed and data remains consistent across both banks? Here is where Oracle Sagas come in. Oracle Sagas provide a framework to implement and administer Sagas for microservices application built using Oracle database. This is the first database implementation of Sagas, a fairly old concept that developers had to code themselves. So, what are Sagas? Think of Saga as sequence of steps, like withdrawing money from one bank account in Bank A and depositing money into different account in Bank B. Each step involves a small local transaction which are committed right away. Each step in a Saga updates the database and sends a message to trigger the next step. But what if something fails? Let's say the remitter's account has insufficient funds. In this case, Sagas come with the power to compensate transactions. Sagas use compensating transactions to undo the previous steps and to ensure everything is clean and consistent. This feature makes Saga a reliable tool for managing transaction across microservices. So, what makes Oracle Sagas the go-to solution? The framework seamlessly integrate with Oracle database and also integrate with existing Oracle technologies like advanced queues, transaction event queues, and also with log-free reservations in database 23C. Oracle Sagas offer multitude of advantages. They eliminate the prolonged locking typical in synchronous transactions. Sagas ensure all participating services either commit or roll back their changes, preventing inconsistencies. With completely asynchronous processing, Oracle Sagas provide scale for transaction across microservices. By building on Oracle database, they also leverage the database's high availability features, making them a sound choice for developers looking for reliable transaction management. Oracle provides a streamlined approach to Saga implementation through specialized annotation that align with the MicroProfile LRA standard, simplifying how developers define and manage distributed transactions. Oracle Sagas extend the MicroProfile LRA specifications by using asynchronous messaging with transaction event queue in the Oracle database. These annotations tell your code how to participate in a Saga and what to do in different situations. Let's discuss some of the annotations. At LRA, at request, and at response. These are invoked at different instances of a Saga lifecycle. At LRA controls the initiation of Saga. At request is used to invoke a method which is responsible for receiving incoming request from Saga initiators. While at response is used to annotate those methods that collect responses from Saga participants. Let's take a quick look at the controller code for the initiator and participant in our banking example. We are currently looking at the controller code for the initiator, Cloud Bank, in our banking example. Here, we have a JAX-RS endpoint defined to receive the REST calls for money transfer. Now, since handling this request would involve initiator and participant bank microservices working together, it would be ideal to initiate a Saga at this point. How do we do that? We use at LRA annotation. The Saga ID for this newly created Saga is inserted into the header parameter. This Saga ID is further used to send out requests to different participants. Now, let's say we started the Saga and sent out the request to one of our participant microservices, Bank A. Let's see how will Bank A handle the request received from the initiator. Here, in the controller code for Bank A, we have a method on request, which is responsible for handling the request sent out from the initiator. So, after receiving the request from the initiator, this method is invoked. It processes the request and sends back the response to the initiator. Let's see how the initiator handles the response. Here, in the controller code for initiator, we have a method annotated with @response, followed by the argument specifying the sender of the response. This method gets automatically invoked when the particular sender mentioned in the code sends back a response. Here, we receive the response sent from microservice participant and process the response to update the database accordingly. These annotations minimize the complexity typically associated with distributed transaction management, allowing developers to concentrate on business logic rather than transaction coordination. We will discuss other annotations supported by Oracle Sagas in future videos. Let's consider our banking examples topology. Here, we observe the strategic setup of microservices within Oracle Saga architecture. These microservices, highlighted in the blue box, communicate via a central broker and are orchestrated by a Saga coordinator. They carry out different parts of the transaction. The coordinator ensures that the entire process across separate databases stays in sync. It actively maintains the global state for the group of local transactions. So, if a transaction needs to be reversed, the coordinator steps in to manage this, ensuring that all parts of the system reflect the correct state of affairs. Unlike traditional XA transactions, where a single lock can hold up the entire system, Oracle Sagas facilitate transactions with more agility. They employ short-lived locks, which are crucial for quick and isolated transactions, reducing the wait time significantly. This approach ensures that even if one microservice is busy, it does not cause bottleneck for the other. Moreover, Oracle Sagas integrate with lock-free reservations, enhancing this concurrency further. This means multiple transactions can proceed independently without locking each other out, leading to higher throughput and efficiency. We will discuss how to establish this topology in more detail in future videos. In conclusion, Oracle Sagas represent a significant leap forward in distributed transaction management, offering a resilient, efficient, and scalable solution well suited for the complexities of modern microservices architecture. They provide a robust alternative to traditional methods, empowering systems with the agility needed to thrive in today's dynamic and interconnected digital landscape. Thank you everyone for watching. Your insights and feedback are invaluable as we continue to explore and enhance Oracle Sagas. Keep an eye out for our next video in the series where we will dive deeper into Saga compensation and simulate different scenarios in our live banking example. Thank you.